Before we launch, we have this phase 0, which is handled and currently operated mainly by us. But you can think of it as the pre-launch registration, where we are collecting all of the public information of the genuine chips on board of the system. We are registering them. After we are deployed in orbit, we are actually launching and measuring the secure boot of the system. We are verifying that the image that we are expecting there is genuine. We are generating the private public key pairs of all of the components in space. Afterwards, we go to the phase 3, which is the satellite execution assurance protocol I was describing, collecting the individual endorsements, and we collect the certification of authorization, which basically allows us to see, okay, this is a genuine TE running on satellite in space, and this is the part that actually afterwards gives us the confidence for every successive communication. And lastly, once we do it, we have the phase 5, which is the virtual station, which basically is happening during the runtime of the system as well. And of course, in practice, you can consider that you want to maybe do this step 1 to 4 on a regular basis, but it's also possible that you don't do it as often. So this is like a matter of configuration and adjustments of the real-world deployments as well. So looking from the design of our protocol, let's also dive into the practice on how are we actually currently implementing it. So we are relying on USB Armor MK2, which is an open source hardware that actually can be easily taken and theoretically also built by you. It has several cool components. One part of the secure boot, where you can actually go and register public keys inside of the registers on board of the USB Armor MK2. It is supporting ARM Trust Zone as a trusted execution environment. So for those that are familiar with TEs, ARM Trust Zone has been around for quite some time. It's not the most flashy and latest TEs, but for the purposes of our use case and actually the extension of our workflow, it's providing all of the features that we are looking for. And it also is implementing 2 dedicated secure elements on board, namely is the NXP SE050 and Tropic Square Tropic 01 chip as well. And something about this quite also interesting for other application and future enhancement, it also supports a hardware-based monitoring counter inside of the secure elements as well. Briefly also providing overview of the ARM Trust Zone. So this is something that I was briefly mentioning. We have the secure world and the normal world, and inside of the secure world we have the different exception levels that allow us to deploy different applications on different levels. And the secure monitor is the part of the TCB is separating between what application is running within what part of the ARM Trust Zone worlds itself, and is handling the overall separation between trusted and untrusted applications. And under it, we have the individual secure elements. We're just providing overview of why we are actually happy to rely on 2 different types of secure elements. One part is a more traditional closed source solution from NXP, but for enterprise clients, it's quite nice because it's already being established by having common criteria EL6 standardization, and it's rather mature technology and it's heavily certified. And on the other side, we have more new technology, but I think providing very cool capabilities, which is the Tropic 01, which is actually based on RISC-V core. It's completely open source in the context of the design and the firmware as well, and it can be basically auditable down to the gate. So very different approaches with respect to the solutions, and with that we are focusing on providing also the mitigation of supply chain threats by having a diversification on the lines of 2 different vendors with 2 different design philosophies, and basically having 2 different type of components that are later on part of the overall attestation flow as well. And the unique feature also of ARM Trust Zone is that you can actually go and attach the dedicated secure elements directly to the secure world itself. So that way the device tree that is actually interacting with the dedicated chips is only available from within the secure world, which is quite a unique feature in itself because of course it means that I can have direct access to these secure elements on board and also use them for additional purposes from only within the secure world as well, which is quite unique, and this is basically part of the overall capabilities that we are trying to unlock as a part of the overall workflow. And this allows us to actually also push this idea farther that at no point in time there are actually signing keys being generated on Earth. And as a part of the initial boot, we are actually verifying that this is the case by checking the status of the gates that are available as a part of the chips. This is being enforced by the image we are using. And we are only registering the respective public information and artifacts of these individual chips before we actually send them to space. So this is part of the setup phase, where for the SE050, we are looking into the factory serial number, and for the Tropic 01, we are looking into the unique identifier on the chip as well. So that basically also opened the question, can an attacker theoretically clone this information that are available? In practice, they can do it, but it will of course mean that they have to go and deploy the particular chip with all of the stuff baked in. But even if they would do it, it doesn't necessarily guarantee the endorsement that will be coming out of the respective ground station, because once the chip is available and it's in the wild, you will be registering the respective key material that's generated in the space, and only afterwards you'll be getting the endorsements from the individual ground stations to basically complete the overall workflow as well. So overall, how does it look like in practice? We have the secure world that is having the connection to the different secure elements. We generate the key pairs after they are in space, and afterwards we are issuing the same workflow, as I mentioned, as a part of the satellite execution assurance protocol workflow. And in this case, we are expanding it by not only a single one, but by both of the dedicated information that are cross-signing each other as well. And something as a fun fact at the end, part of the TE lifecycle is, of course, what happens after I decommission my particular server. In space, it's quite easily solvable. Maybe it's a feature or a bug, depending how you look at it, that once the satellite lifetime comes to the end, it has to burn in the atmosphere. So in that sense, it's basically enforcing the end of the lifetime, because basically once the satellite itself is decommissioned, it will basically burn all of the key materials on the way through the atmosphere as well. So this is quite an interesting property with respect to that, because of course for the overall life cycle, when you look at hardware on Earth, it can sometimes be challenging to decommission all of the properties, but this is something that is being enforced by the space itself. And something what we are very happy about, just briefly, we are bridging the design to reality, and the Space Fabric architecture I was describing will go live later on this year on our first mission, where actually we'll be launching the satellite with the respective capabilities I described later on this year around Q3 as well. So we are excited to bring the idea to life as well. So with that, I would like to thank you, and if you're interested, get in touch, and we'll be happy to take any questions from you. Thank you very much.